Hello everyone, my name is Jong-ik Kim, and the paper I'm going to present is Boosting Graph Similarity Search through Pre-computation. Informally, graph similarity search is to find all graphs in a graph database that are similar to the query graph. It is an important access method used in a wide range of applications, such as image analysis, drug design, malware detection, and so on. To quantify the similarity between graphs, we use graph edit distance, GED in short. The GED between two graphs is the minimum number of graph edit operations to transform one graph to the other graph. A graph edit operation is an insertion, deletion, or relabeling of a single vertex or edge. For example, let's consider the two graphs G1 and G2. The hollow and solid lines in the graphs represent edge labels. The graph G1 can be transformed into the graph G2 by relabeling the edge between A and B, inserting a solid edge between B and C, and deleting the edge between C and D. Therefore, the GD between the graphs is 3. GD precisely captures the structural difference between graphs, and it is applicable to all types of graphs. However, the disadvantage of GD is the computational overhead, because GD computation is NP-hard. The problem studied in this work is to find all graphs in a graph database whose GD from the query graph is within a given threshold. We aim at developing techniques for efficiently evaluating similarity queries on large graph databases. Existing work adopts the filtering and verification paradigm to evaluate graph similarity searches. In the filtering phase, filtering conditions are established using features of graphs, which are substructures of graphs. Each candidate graph surviving from the filtering phase is verified through GD computation. To reduce the overhead of GD verification, the main focus of existing techniques has been on developing effective feature-based filters. However, we empirically found that the feature-based filtering has an inherent limitation. The filtering effect sharply decreases when a GD threshold increases. As a result, the number of candidates grows extremely faster than that of results, as shown in this figure. Motivated by the empirical results, we will use pre-computed similarities between data graphs in generating candidates. Let's see how we can use similarities of data graphs in generating candidates. Consider a query graph Q with a GD threshold tau. Since GD is a metric, for the ease of presentation, I will describe the basic idea with an illustration in two-dimensional space. The circle shows the result space of the query. Given a result graph G such that the GD between Q and G is delta, our first observation is that the result space of the query is included in the red circle, which denotes the space for the graphs whose GD to the graph G is within tau plus delta. The second observation is that the result space of the query includes the blue circle, which is the space for the graphs whose GD to the graph G is within tau minus delta. According to the observations, we can generate candidates using the result of similarity search for the graph G. Moreover, some candidates will be immediately identified as result graphs without verification. To exploit our observations, we need to know the similarity search results of data graphs. So we use pre-computed pairwise GEDs of data graphs as an index to develop our search framework. The figure shows example data graphs and index for the graphs. Assuming we have an index, we can evaluate similarity queries as follows. Given a candidate set C, which is initially contains all data graphs, we verify each candidate via GED computation. Whenever we find the result graph, based on the first observation, we first generate another candidate set C prime using the index. Then we collect results from C prime based on the second observation. Finally, we refine the candidate set by taking the intersection of C and C prime. Now I will present our GED computation algorithm. The GED between two graphs is computed by enumerating vertex mappings from one graph to the other graph. For example, possible vertex mappings between G1 and G2 can be enumerated as follows. The vertex mappings are organized into a prefix tree, which is called a search tree. Each intermediate node indicates a partial vertex mapping as shown in this figure. While traversing the search tree, we compute our GED lower bound at each node. And if the computed lower bound is greater than the threshold, we can reduce the search space by pruning the subtree routed by the node. In general, the tighter the lower bound is, the more subtrees we can prune. To compute a lower bound of a partial mapping, we decompose each graph into three parts and compute the number of required edit operations in each part. For simplicity, we call the number of required edit operations the edit cost. We first compute the edit cost in the mapped part. Since we have mapping information for the vertices in the mapped part, the edit cost is exactly computed. Then we compute a lower bound of the edit cost in bridges, where a bridge is an edge connecting a vertex in the mapped part to a vertex in the unmapped part. This lower bound is relatively tight because we can partially use the mapping information from one endpoint of each bridge. Finally, we compute a lower bound of the edit cost in the unmapped part. To compute the lower bound, all existing solutions use the label-based lower bound, which simply counts the differences of labels. Because the label-based lower bound does not reflect structural differences of the graphs, it tends to be very loose. Therefore, the goal of our work is to tighten the lower bound of the unmapped part. To tighten the lower bound, we use two more existing lower bound methods. The first one is compact branch-based lower bound, which can capture the differences of local structures. The second is the partition-based lower bound, which can capture global structural differences. This is the proposed lower bound function for a partial mapping M. We first use the label-based lower bound for the unmapped part. If we cannot prune the subtree routed by the mapping M, we try the compact branch-based lower bound. If we still cannot prune the subtree, we finally apply the partition-based lower bound to the unmapped part. Although feature-based filtering techniques have limitations as we've seen before, we have observed that they can be effective in filtering dissimilar subgraphs while computing GED. We can seamlessly integrate the filtering phase into GED computation by applying our lower bound function to the root node of the search tree. Please see the paper for the details. Although our lower bound function can tighten the lower bound of a partial mapping, it requires more computation for the lower bound of the unmapped part. Interestingly, many partial mapping shares the same unmapped part. For example, the two mappings M and M' in the figure shares the same unmapped part. So we can save the computational result of M and reuse it for M'. Now I briefly introduce how we build an index containing pairwise GEDs of data graphs. To build an index that stores pairwise GEDs, we assume a predefined maximum threshold tau max. It is reasonable to limit the maximum threshold because GED is very sensitive to small differences between graphs, and applications consider practically small threshold only. If a large threshold is required, we can use a coarse-grained similarity measure instead of GED. Given a maximum threshold tau max, we need to compute GEDs within 2 tau max by our first observation. Therefore, index building is in fact the self-join problem with a threshold 2 tau max. We note that an index is built offline, and many online queries take advantage of the index. Nonetheless, excessive indexing time prevents the proposed technique from scaling to a large database. The following are the problems in indexing and our solutions. The first problem is that GED computation with 2 tau max can be too costly to be practical. To alleviate the problem, we restrict the threshold for indexing to tau max plus C, where C is a small value. Please see the paper for the details of adjusting the parameter C. The second problem is that GED computation for a certain pair of graphs can be intractable due to the NP hardness of GED computation. To solve the problem, we allow inexact entry for a pair of graphs requiring excessive GED computation time. In this case, we save a lower bound of the GED instead of an exact one. Please see also the paper, how such a pair is detected, and how a GED lower bound of the pair is computed. The third problem is that we need similarity search results for all graphs in a database. Since similarity searches for different data graphs are independent, they can be naturally parallelized. So we implemented parallel and distributed index construction for the problem. We also tried sampling data graphs to be indexed, and observed that careful sampling can significantly reduce the indexing time while retaining good performance of query processing. Incremental indexing can be used with the sampling approach, so that index entries for missing graphs are added whenever necessary. We conducted experiments on an Intel machine running on Ubuntu OS. For distributed index building, we used 5 similar machines. In experiments, we used 2 real datasets, ACE and PubChem. We randomly selected 100 queries from each dataset to evaluate the proposed technique. We excluded the selected queries from the datasets because our technique immediately returns all results as soon as it finds a graph identical to the query graph. To evaluate GED computation performance, we compared our algorithm NAS-GED with 3 existing algorithms: A star plus LSA, INVEST, and CSI-GED. To evaluate NAS, our similarity search algorithm, we used 2 existing indexing techniques, parse and ML index, which are combined with the INVEST verification algorithm. This is the result for indexing times. On both age and PubChem datasets, the indexing time linearly decreases as the number of distributed nodes increases. The second table shows comparisons of indexing times with the 2 representative indexing techniques, parse and ML index. ML index could build the indices very fast, while parse consumed enormous time for indexing. The proposed technique NAS with 5 distributed nodes required reasonable indexing times comparable to ML index. This is result for GED computation. In this experiment, after applying a Bayes filtering technique to the datasets, we directly verify remaining graphs through GED verification algorithms. On both datasets, A star plus LSA was the best performer among existing techniques, and our algorithm NAS-GED consistently and significantly outperformed all existing techniques. NAS-GED was up to 3 times faster than A star plus LSA. This is result for similarity search. Our search algorithm NAS significantly outperformed existing techniques. On the age dataset, NAS was from 4 to 15 times faster than existing solutions. On the PubChem dataset, NAS was up to 100 times faster. In this work, we observed the limitation of existing feature-based filtering techniques and proposed a completely different approach to graph similarity search. We used pre-computed pairwise GEDs of data graphs in generating candidates, and verify each candidate using a new GED computation algorithm. In the experiment, we showed that the proposed approach significantly improved the performance of graph similarity search. Thank you for listening.